Okay, find I, where I is the integral of the square root of 4 minus x squared dx. So this one, there's nothing like it in the table of integrals. We're going to use a little bit of, experience here. So looking at that 4 minus x squared, I'm not immediately aware of anything that might help us here. However, with a bit of thought, maybe a little flash of luck as well, you think, well, what's something that looks similar to that? Pythagorean identities involve something minus something squared. Maybe we could use a Pythagorean identity here. And that's what we end up doing. So we make a substitution that turns this into a Pythagorean identity. And so the substitution here is to replace x with something else. So in all of the other substitution integrals that we've done, we've said let u equal something to do with x. But this time I'm going to let x be something else. I'm going to replace x with another expression. So I'm going to say, I'll need a bit of space here, let x equal, now we've got a 4 here, so I want to make sure that whatever I replace x with, I end up, when squaring it here with the x squared, I end up with something involving 4, so I can take 4 out as a factor. So I'm going to say let x equal 2 sine theta. That way, when I square it, I'll get 4 sine squared theta. Now, we need to work out what dx is. Let's do it over here. Dx d theta will be 2 cos theta. And so dx is 2 cos theta d theta. So now I. Alright, so now everything is in terms of theta. And we can do a little bit of tidying up here. The 4 could come out as a factor. When you take 4 as a factor outside of the square root, remember it won't stay a 4, it'll become a 2. So I'll have 2 coming out from here. I've also got 2 over here. So the 2 that's coming out from here and the 2 that's coming over from here gives me 4. So I can rewrite this with the 4 out the front. And now we're in a good situation because 1 minus sine squared, remember, is a Pythagorean identity. I can replace 1 minus sine squared theta with cos squared theta. And we've got the square root of cos squared theta. So it'll all tidy up quite nicely. And so that gives us and now we can use our double angle identity here, because cos squared theta is a half 1 plus cos 2 theta. Now here's our answer from earlier, but remember our integral is in terms of x and we need to get it back in terms of x. So look here where we made our substitution, let x equal 2 sine theta. So we can say, alright, so now x equals 2 sine theta, alright, so sine theta is equal to x on 2. Okay, so if we drew up a triangle that had this as its property, we'd have something like this. And and we'd need something on the bottom there. Okay, so let's do that. That's our adjacent. So using Pythagoras theorem, we're going to get 2 squared, so 4 equals x squared plus a squared minus x squared. So our adjacent is that. And so we will replace that in our diagram. And we've got that. So, what is theta? So now, looking at our answer, we've got 2 theta plus sine 2 theta. Let's look at that. So our integral became 2 theta plus sine 2 theta. Now, remember sine 2 theta can be written as 2 sine theta cos theta. And we're going to get sine theta and cos theta from our diagram. First of all, theta is, we know that sine theta is x on 2. So theta is inverse sine of x on 2. So we're going to get 2 times inverse sine of x on 2 plus 2 times sine theta. What's sine theta? Sine theta is x on 2. I'm running out of space here. Oops. Times cos theta. Now cos theta is adjacent on hypotenuse, so that on root 4 minus x squared on 2. So times cos theta, which is root 4 minus x squared on 2. So putting all that together, we get 2 inverse sine of x on 2 plus the 2's are going to cancel here, and we get x root 4 minus x squared 2's on 2 plus c. And there we are.